Hello, welcome, and a very good evening to another Let's Code x86 assembly episode. Today we have a special episode because I'm not taking an example from Oscar Toledo's brilliant book, Boot Sector Games, but we will do our own Sizecoding thing with a little bit even more advanced techniques, I would say, in a way. Some things that we haven't touched yet, graphics programming, for example, even a little bit of MIDI music, if we can call it that, stuff like that. And we will restrict ourselves to even lesser size. Oscar's examples are supposed to fit into a boot sector of a diskette, that is 512 bytes. But there are other size coding competitions where you can code for 256 bytes or even 128 or 64. You can go as low as you want. I mean, at some point it stops being a useful program. But we are looking here at a 256 byte program. Actually, at the moment it's 254 bytes. So we even have 2 bytes left over. And I'm not gonna build it up step by step, but we'll go through it and I'll explain it on the way. Because the way I arrived at this was to basically just code what I wanted to see and then trying to reorganize the code and use different instructions to make it smaller and smaller and shave off a byte here, a byte there, until I ended up with less than 256 bytes. I tried to enter this into the outline demo competition for 256 byte intros. Outline is a demo party in the Netherlands. However, contrary to the last couple of years where you could just enter remote entries, I think this year was only probably for in-person event. And we've been to Revision this year, which is another demo party, but I couldn't make it to outline due to family stuff, so I tried to enter remotely by sending an email to the organizers. Sadly, I didn't hear back. I guess they had their hands full with other stuff and my entry never showed up, so I guess they just silently ignored it, didn't get the email, I don't know. Was a bit sad, but yeah, that's the way things are. But instead, you guys and gals are going to profit from this because you will see what this thing looks like. And the topic today is the game of life. For all who don't know what the game of life is, it's something that our good friend John Conway, may he rest in peace, invented. It's a so-called cellular automaton with a few simple rules that I won't explain today, except in the parsing while explaining the code. You can create very complex organisms or structures that replicate and run basically like this. Here, for example, is a so-called glider gun where cells create these little structures here that move off into the distance. It's being computed on a two-dimensional grid, which is no problem for us here. And we are targeting, obviously, the 8086 processor, as you can see here. So it will run on very, very old CPUs, but it will be very slow because it's actually very computationally intensive. We will compute the game of life from a certain starting condition. I'm trying to find it here. There's one very nice starting condition called the Acorn. Let's see. Ah, yeah, here it is. This is the starting configuration that we're taking because it runs for over 5,000 iterations without any repetition, basically, and it looks very chaotic. And it only takes up 7 cells on the grid for the starting condition. We will also show the game in a slightly more fancy way. The cells that are alive and then die will not immediately vanish, but they will fade out. Cells are black and then they will fade out into gray and white over time, so that it looks nice. Also, we will have some kind of MIDI music. And I tested this actually on my True 486 on the Roland MT32. It works. But here we'll use DOSBox with an emulated MIDI interface. And yeah, as you can see, live.com currently is 254 bytes. The source code is much bigger because I also have a lot of comments in there. And let's just run it for a couple of seconds so that you can see what it does. We also print out my handle, root 42. And it also reacts properly to the escape key to abort and go back to text mode. So it does a lot of things. Initialize graphics, initialize music, compute the game of life with the fading effect, and produce some kind of music. The notes are proportional to the amount of currently living cells in the game. So a very low note basically means very little alive, and a very high pitched note will be a lot of alive cells. So let's listen to this. Earphone listeners beware, it might get a bit loud. Okay, I think that's enough for now. Yeah, I think it's a pretty artsy thing to witness. Also, you saw these diagonal streaks. Those are actually gliders that are produced by Acorn. These are these structures here, which you can't really see because they will just be fading out diagonal lines. That's a bit of a disadvantage that you can't really see the structures, but I think this cloudy appearance, this ink-like appearance looks actually pretty nice, so I left it at that. And let's load this up in the debugger so we can have it here in the background comparing how many bytes certain opcodes use. And then I'll go over to the Emacs here, where is it? And explain the code line by line, basically. Yeah. And we can have a look at the actual bytes that are generated by the assembler. I will explain the constants maybe just very quickly. Old gen and new gen are the data segments where we store the two different generations that we have to keep track of, the last generation of Game of Life and the current one. And these are basically just the segments in memory. Actually, this would be the segment 4000, and this would be the segment 5000, but we only need to store 1 byte because the lower byte will always be 0 anyway. So there are a couple of assumptions. You can Google some size coding tricks and you will find a page that explains how the status of the registers in MS-DOS are after the program loads, and you can have a few of those assumptions. For example, that all the segment registers have a 0 in the lower byte, so we only need to use the high byte. The stat port is the status port of the MPU interface, and that is hexadecimal 331. At least in our case. If you have something different, you need to adjust this value, but usually all the MPU interfaces are listening to 330 and 331. But let's start here. Set up the graphics mode in the palette. This is something that we already know from our other Let's Code MS-DOS series. We load hexadecimal 13 into the AL register because for the graphics interrupt, which is interrupt 10 hexadecimal, this means we are switching to VGA 320 by 200 by 256 colors mode. And we can already assume here that AH equals 0, because this means that we only need 2 bytes here, B013 for the instruction MOV AL13. If we had also tried to load AH with 0, because we need to use function 0 of interrupt 10, then this would have been at least 1 more byte, or 2 more bytes if we split this off into a different instruction. And that is already one of the tricks. We assume that AH is 0, which is the case under MS-DOS after the program loads. Then we load the VGA palette register, the index register, into DX, because for an out instruction you need to load the port address into DX. That's how it works. Then we are clearing the AL register, and we could have also done MOV AL, 0, but depending on your assembler, XOR AL does the same thing in less bytes, because an XOR of the one register with itself will clear that register because it's an exclusive OR. So exclusive ORing one value with the same value will always result in a 0. And this is also one Sizecoding trick that you can do. I tried to write MOV AL, 0, and it would give, I think with NASM, it gives the same opcode because it knows about this optimization already. But for clarity, I'm using this here, and now it doesn't matter which assembler you use. And funny enough, out DX AL is a very short opcode, it's only 1 byte EE. Which means we are setting the whole VGA palette, so we need to tell the VGA card, let's start at color index 0, and then write that color index to the VGA register, and then we're going to the VGA data register for the palette, which is 3C9, and we're not doing a MOV, but we're just doing increment DX, because then DX will be 3C9, obviously. And then we're starting with the color white and using the CL register to do that, because it's only an 8-bit value. Actually, it's only 6-bit, so 40 is the maximum that we can have, and we are writing out all the stuff. And then we are decrementing the value and writing the R, G, and B values to the DAC register, and then looping. Okay, I think I'm yeah, there's one more great trick. Exactly, I surprised myself here. We are writing out the RGB values, which at the moment will be white because we loaded the 0x40 into CL. But the fun part is we can use the 40 here also as the counter, because we're doing loop, and loop will decrement CL, compare if it's 0, if not it will jump to init palette. And then the next time it will use the decremented AL value. And that's a bit sad that we can't use out DX CL, because then we could have saved this little instruction here, which is FEC8, that are 2 bytes, because the loop already does a decrement. And I think even a MOV ALCL would have been longer, I think. I think that's also a 2-byte opcode. So there is probably not something shorter, but we can look that up. Let's see if this thing here also shows us, this is Felix Cloutier's website. I think it might be that it shows us the opcodes themselves. Does it? Probably not. Well, we can have a look. Let's try that. Let's see what happens. MOV AL, CL instead of dec AL, but it's probably not helping. Let's call up a terminal and then assemble this. It's still 254 bytes, so that doesn't change a thing. That's also a 2-byte opcode. Okay, doesn't help, but nice that we tried that out. And that's something you would do all the time, testing opcodes against each other to see which produces the shortest amount of code, basically. And yeah, that's how we end up at this stuff. Okay, so now we've initialized the palette, going from white to black in the course of 63 or 64 colors. And we don't use the rest, the 192 other VGA colors we don't use, because we don't have more grayscale resolution than that, because VGA uses a 6-bit palette. Okay, next up is loading the buffers for the generations. So here we are saving again on a byte by just loading the high register part of the CX register, CH, with the old generation constant, and then moving it to ES, but as CX completely. And you can't load this immediately, because segment registers can only be loaded via a different register like CX, for example. If there's a shorter version, please leave it in the comments. I'm always keen on learning how to shave even more bytes off there. Let's have a look. Yeah, that's 2 bytes we have here and 2 bytes there, so it's 4 bytes just to load that stuff. There's also the possibility to push a value onto the stack and then pop it to the register, but I think that doesn't help here, because we would need to push a 16-bit value and pop a 16-bit value, which gives us a similar performance here. We pop the register, which is I think 1 opcode, but we use 3 opcodes here, because push 4000 will be 3 bytes and this will be 1 byte. So in the end you stay the same. And another disadvantage is if you use push with an immediate value, this won't run on an 8086, but you need at least an 8186 or 8286, because they introduced this. So in short, the same could have been used like this, 0x4000 and then pop ES. Would have done the same as these 2 lines, but this is only 186 and 286. And we don't want that. We want to limit ourselves even more, so that's fine. Okay, then we need to clear the buffer. I'm loading the CX register again with the number of bytes that we want to clear. Again, we assume that CL is 0, which is true, and we're loading FA is I think something like 64 or something like that, because we need to clear 300 by 200 pixels, 64,000. Then we need to clear the destination index, because ESDI will be used to store whatever is in AL, I think, maybe? Yeah, I think so. And rep stores B repeats the store string byte, and it will increment automatically ESDI to progress. This is a fun way to clear a buffer, basically, in a relatively short amount of code. As you can see, 2 bytes for clearing the destination register, 2 bytes for loading the number of bytes that we're doing, and then 2 bytes for looping. That's 6 bytes to clear a whole buffer. Again, if you have an even shorter version, that would be nice to know. Then we need to load the DS register with the same value, so we just push ES and pop ES. Here it's okay, because those are 2 1-byte opcodes. That's pretty efficient. And then we need to load the new generation onto the stack, which we will always use. We exchange the new generation pointer with the old generation pointer and do a kind of double buffering that way. So that's pretty straightforward. Again, we load CH only, not CX, because that's too expensive, and then we push CX onto the register, onto the stack, and will not do a thing with that. And now we get to the sound. We need to reset the MPU 401. There's a couple of things to know for the MPU 401, and this will only work with true MP401s, which you can emulate in DOSBox, or for example I have the PC MIDI card, and they start up in so-called intelligent mode, where they are basically behaving like a sequencer, a MIDI sequencer, and very complicated, but we just want to send MIDI notes. So all we do is, I'm gonna skip over this subroutine for a second. We are sending them a command called hexadecimal 3F, which is the switch to UART command. So they behave basically like a serial port, and write that to the status port of the MPU. Funny enough, after this call MPU is output, we will have DX loaded with the correct address. So MPU is output is one function that we need to have a look at very quickly. It's a very simple function. It reads the status port. So at the moment we always assume that DH is 0x03, like this, hexadecimal 3. And this is always the case because all our ports that we are writing to are in the 300 range, and we don't do anything with the DX register apart from this. And we have to read that status bit with the in command, and then we have to test for the 7th bit, which is 0x40 hexadecimal. So we are ANDing this, and this will result in AL being masked basically, and then returning more or less. And this status bit means that if it's 0, it means the MPU 401 is ready to receive stuff. Otherwise it's in output mode and it's busy basically. So we are doing a short loop here. And on certain hardware this will hang in the emulated fashion, and on my MPU it worked just fine. You should put a timeout here like a counter, but we are Sizecoding, so we don't care about that. If it hangs, yeah, out of luck. That's just to note here. Okay, quick break, taking a deep breath, and next up we can continue on our way by setting up the Acorn starting condition, which was down here. Just to remind you, we are putting it somewhere on the screen, putting one thing down here, then going down one line and 2 to the right and plotting something, then going down another line but a bit to the left and putting in 2, and then going to the right and putting in 3. Yeah, and at first I figured out this is the way to do that with MOVs, with bytes and words, because these double pixels basically can be done by writing words, which is more efficient in a Sizecoding aspect, and the single bytes can be done by a MOV byte. I leave it up to you as an exercise to understand this bit here, but I found an even shorter version basically, because we can get rid of these complicated arguments here, which will result in 16-bit values being put as literals in there, and this is a very expensive expression here. It takes a lot of bytes to assemble this, and it's actually much easier to set up the destination index register with the initial coordinate, which is 320 by 100. So I'm going to the 100th line and then to the 161th pixel in that line. So basically smack in the middle of the screen, which would be coordinate 100, 160. And I'm setting the pixel there by storing a byte there. And this will automatically write to ESDI, but it's a very, very short opcode. Let's have a look here. Going here, exactly. So storing a byte is AA, and later we're doing storing a word, which is AB, so only 1 byte instead of the very complex thing here. And after that, of course, DI gets incremented, and we need to increment it more by 1 line plus 1 pixel in this case. So we're adding 321 to DI, etc., etc. Doing the stores B again, doing the skipping to the next line, and then we can also do store a word, because we loaded AX with 2 pixels, 0, 1, 0, 1, and we can write 2 pixels at once with only one single byte, which is basically very cheap. And yeah, as you can see, this is actually pretty neat. I'm thinking if we can make this add di even shorter, but I think an increment di is probably also not a 1 byte opcode. We could try to, let's see, to replace this with inc di, but I doubt that it's any better. Let's see if I can crank up the volume here. Oh, actually it does work. Yeah, let's open this again. So nice. We found another way to make this even shorter. That's nice. Yeah, yes. Oh yeah, it's only 2 bytes instead of the 3 bytes we needed for the alternative. See? Skip 2 cells can be done by incrementing di. That's cool. Now we have even more bytes to spare. We can probably code a whole nother feature into this program. All right, that's that. Now we set up. Are you still with me? It's a lot to do. Okay, let's do the main loop. That's a bit easier perhaps. We need to set up the counter again. Again, we're only doing the high byte. Again, we're doing 64,000 pixels. That's fine. We need to take the other buffer from the stack. This is basically the double buffering. So we pop ES. Then we clear the source register because we will do some kind of loading of the data. Again, not with a MOV, but with a load SB string byte thing. And we need to calculate how many pixels are there in the 8 neighborhood around our pixel. Basically, the 8 neighborhood is, it's actually pretty simple, right? Let's take this pixel here. So the 8 neighborhood is these 8 pixels around that. We need to count how many pixels are in there. And the rules are pretty simple. Any live cell with 2 or 3 live neighbors survives, so it stays on. Any dead cell with exactly 3 live neighbors becomes a live cell. Exactly, not 2, not 4, but exactly 3. And all other live cells die. And our other dead cells stay there. That's simple. So basically you need to figure out 2 or 3, it lives. Exactly 3, it lives. Else kill it. That's pretty simple. And how do we do that? That's a whole lot of shit here. Sorry for the expletive. But it's something that I didn't get any shorter. I would have loved to get this shorter, but maybe you find something. AH will be the sum that we calculate. And I need to load the current pixel position, which is the counter, which goes from 64,000 down to 0. And then I need to go to the first pixel, which is 1 line up and 1 to the left. So I subtract 1 line, 320, and 1 pixel to go 1 left. And then I load the first pixel, which will automatically go to the next pixel because load string byte also increments di. Then I add to my accumulator, which is AH, the value that we just loaded into AL. And I'm not sure if there's a shorter thing. Let's see how short that actually is. It's 2 bytes, and I'm wondering if there's a 1 byte opcode to do something similar. Probably not, because the add is already extremely short. I don't think there's something. Again, leave a comment if you know any better. And basically this goes on like that. Sometimes we have to skip to the next line. And yeah, that's it. And here are the rules actually. These are all the rules that we have. We have to compare our accumulator to 3. We have exactly 3 neighbors. Then we will create a cell. And it's important to do a short jump here because it will decrease the size of the opcodes. There will be only an 8-bit, so 1 byte offset basically. If we have 2, we are executing the command keep cell or the subroutine keep cell, and otherwise we will delete the value in AL and just call store cell, which will basically kill the cell because it will set it to 0. Okay, create cell basically loads AL with 1 instead of the AL that we have here. And I don't think I get around this immediate thing here because this is, let's go down. Exactly this one here, this is 2 bytes, and I don't think you can do this any shorter because XOR AL also takes already 2 bytes, and an increment would not help. So this is pretty short already. I don't think there's any better way to do that. And then we also call store cell, which depending on if there's a 0 or 1 will create or kill the cell basically. Keep cell just does a load SB, and store cell does the store SB, which basically copies the cell basically if you do the keep cell thing. And I think that's pretty neat. There's a bit of resetting here and there, like the source source index will have to be reset and stuff like that. But yeah, I think this algorithm is pretty decent, and it will loop around to go over all the 64,000 things. Okay, now comes a bit more magic. Another quick break, take a breath, copying to the screen and doing the fade out basically. So we are storing the current buffer for the generation on the stack again, and then we're loading the VGA segment into ES instead, which means it's the A000 segment. And again, we are just using CH and loading that. I'm not sure if I could do this any shorter, but I think this is already pretty optimal. We need to clear BL, SI, and DI for the copying of the data into the VGA memory. And this is the accumulator that we use for the note pitch, I think, for the MPU 401. Okay, setting up again to copy 64,000 pixels. We already know that, and then we are copying basically by loading one string byte from memory, then testing if it is 0 or not, test AL, 1. Actually, this pixel 1 I should have written. Jump if not 0 to set pixel, then if it's not, then the pixel is fresh. And yeah, there's an opcode I have to quickly interlude, which is called SCSB, which is scan string byte, which we could use, but the problem is because it does something similar to MOV AL ESDI, which loads whatever is at address ESDI, which is our destination basically. And we're comparing if that pixel is 0 or not. And the scan string byte does that, but also does an increment DI afterwards. And we don't want that. We need to decrement DI, and I tested using that, but it will make my code larger, so it doesn't help. If anyone has an idea how to do that anyway, I'm free for that. So what we need to do is to see if the current destination pixel is 0, then we don't need to do anything, we just continue the copying. Otherwise, we take whatever we loaded, decrement it. This is the fading effect. If the pixel is not 0, it will have some kind of shade of gray or black, and we will just make it 1 less. And we have to check for 0, otherwise we will wrap around and it will look very weird. So once it reaches 0 and is white, it will stay white. Okay, setting the pixel is pretty simple. When we set the pixel, we increment our count of how many alive cells there are, which is the note pitch for the music. And we will, if it's a new cell, it will have the value 63, which is 3f hexadecimal, so it will be pitch black. And then we have the continue copy loop, which will just store the value of EL, and it will update the ESDI. as said, and that's where this thing comes in, where the increment would have been, we would have had to do the decrement of di, otherwise the store speed will do garbage here. And then we will copy. This will go on 64,000 times until all the cells are copied and all the dying cells are being faded out. And then we go to the sound. The sound will play three notes, it says. Actually 3 bytes of sound data. And we load into the source index the sound data pointer, which is down here. One note in MIDI, the minimal note, contains 3 bytes, which is 0x90, which is some note on channel 0 here for our case. And then will be a pitch byte, which is our number of alive cells from 0 to 127. Those are the notes that MIDI can play, and the full range, and the velocity. And I'm picking just some value here for the velocity of the note. This will be always the same. The only thing that we will do is we will overwrite this value here, the 0x20, with the pitch that we stored in BL. Let's see how we do that. Let's go up here. We are almost done. We will make sure that whatever we had in BL is at maximum 127. So we're masking all the 8th bit, because otherwise it will be an invalid pitch. And then we are overwriting that sound data at that position. Then we have to check again if the MPU is ready. If not, we will loop. Again, there should be a timeout here, but we can't afford that. Then we go to the data port, which is the next port, basically, over the status port of the MPU. And then we load the next node, and we have to prefix this with CS, because otherwise load string byte will load from the data segment. But you can put CS in front of here, which will increase the size of the generated code. Let's see what it looks like. Usually load string byte is just AC, but if we go down here, there should be the here, load string byte with the CS prefix. Here it's written as a suffix, which will be 1 byte longer. This is the price we have to pay to load from the code segment here, because that part is at the code segment, because DS and ES are not equal to the code segment anymore. And then we write to the MPU and we loop. And W1 is the number of nodes that was W1. No, W1 is the label, of course, but CX was loaded with 3 bytes in the node. The rest is also pretty straightforward. Printing out the message. We need to initialize a couple of registers. We again using the interrupt 10, and here we're using function 13, which prints characters only and doesn't move the cursor. We load into BL the color, and 3F is in our newly set palette black. You could choose something different, and we assume that BH is 0. And we load the length of the string, which is greet length. It's 8 bytes down here, you can see it. The 0x03 are the hearts in the ASCII table, then root 42 and 0x3 is again a heart. And the whole length is 8. And then we also have to set the position. We are positioning it in row 3 in column 17, and here's the fun part. Because we have DH being set to 3 for all the ports that we're using, we automatically get it to be positioned in row 3, and we don't have to load a whole 16 bits. Again, we saved a byte. Yeah, okay, then we have to do at least a little bit of register swapping. We have to push ES, push CS, and pop ES for loading CS into the ES register, because that's what the interrupt 10 once, maybe there's a better way. Then we call the, we also have to load the base pointer with the greeting address, etc, etc. Call the print function and then restore ES. It's a lot of work to get the characters on the screen, but yeah. So again, if somebody knows a shorter version that works in graphics mode, I'm all for it. The last things we need to do are checking for the, not checking, but doing the double buffering, which means we have to fetch the other buffer that we have put on the stack into CX, because we can't load it directly into DS, that would override it, push the value that we currently have in DS, and then move the temporary CX into DS, basically. Okay, that's that. I think we can't do it any more efficiently. Again, please leave a comment, etc, etc. Then we need to check for the escape key. So we read from the keyboard port, which is 60 hexadecimal. Escape has scan code of 1. This is a well-known Sizecoding trick. So we just decrement AL, which will set the 0 flag if escape key has been pressed, because escape key has scan code 1. If we decrement, it goes to 0, and the 0 flag will be set. And if it's not 0, then we jump to the main loop. Very simple. Otherwise, the key was pressed to quit. So we load function function 0 with text mode, which is video mode 3. We call the interrupt 10 again, just to clear the screen very nicely. Many other intros don't do that, they just leave the graphics on screen, but I don't like that. So we actually spend a few bytes here and then call int 0x20 to return to DOS. There's often the suggestion to just do a ret, which is a 1 byte opcode, but it doesn't work here because we still have things on the stack. So we just call interrupt 20, which works fine. And that's it. That are all the 256 bytes. And I've shown you how to do some magic, I hope, especially by using the string manipulation things like load string byte, store string byte. There might be some more potential in here, but this is all I had for the time being. And yeah, I'm definitely gonna keep on doing size coding because I think it's a lot of fun to understand how the opcodes work. And I hope you could take away a little bit of this. I know that it's a lot. I will put a link to the source code in the video description, so make sure to check it out and play around with this. Maybe you find some more stuff. As I said, the DOS box has to be configured as a SVGA or VGA only machine with a MPU 401 in intelligent mode. And you can then configure it also to use your system's software synthesizer, at least on macOS. That's relatively easily possible. Let's check. I think I have the DOS box preferences here, and let's try to show it. So my DOS box is currently configured for VGA only, which is a relatively accurate VGA emulation. And I think MIDI is set, MPU 401 is set to intelligent. On the Mac you can set the MIDI device to core audio, which will send it to the software synthesizer, which will always work, and it will play piano on channel 0. On Windows you will be able to use something similar, probably Win32 or something, or default. Yeah, you can try it out. And this way you can even get this weird music here, which I'm gonna turn out immediately again, but you can check it out. And yeah, as you can see, it's still running here pretty nicely indeed. You will need quite a few cycles. So this is currently, I think, something like a Pentium 90 or something. So pretty strong machine is needed because you're doing so many operations per pixel. There's no checking how large the area is where active cells are. You can clamp basically the number of pixels that you need to compute, and there are other strategies, but it won't fit in 256 bytes, I think. So this is pretty nice. Yeah, but that's it for today. Share, like, and subscribe as usual. You can support me. Stuff and links are in the video description. Leave a comment, give some hints on how to do better size coding, and hope to see you next time, and so long.